Good afternoon, everyone. We will start the session.
Good afternoon, sir.
Welcome to the fourth week of the course Air Pollution and Control. I hope you have gone through the lecture material. We'll see the practice assignment based on the content of this week. I'm Abhishek Raj, a PMRF scholar in IIT Madras. We'll start with the overview. We'll see the overview for week four. We'll have around 20 questions in the practice assignment. We'll see both theory as well as numerical questions. Then we can take the doubts. Starting with the overview for this week. This week was five lectures. We started with the Gaussian plume models. The assumptions were discussed of this model. What is the framework of this model? What is the purpose to measure the dispersion of air pollutants? Then the advantages of using this model and what are the demerits of using this model were discussed in the final part of lecture one. Moving to lecture two, it was about the was continuation of lecture one. So Gaussian plume models. So what are the different line and area sources related to them? Then alternative methods that can be used instead of using GPM models that was discussed. Like coming to lecture three. So some of the examples were discussed from the GPM. Some numericals were discussed in this. So not much of theory content in this lecture. Uh, some discussion was done on point, line, and area sources. Moving to lecture four. So the topic of airshed was discussed. So we'll have some questions on this also. Delineation, what is the capacity of a airshed? Coming to the final part of lecture four. So a case study was discussed for airshed and some conclusions and inferences were made. Finally, in lecture five, the topic of emission inventory was discussed. So we'll have questions on this also. We'll discuss this topic. And finally, the types and what are the guidelines for emission inventory that was discussed in lecture five. So this was a broad overview for this week. So starting with the practice assignment. So we'll have 20 questions. We'll do polls on each one of them. So I hope all of you will answer in the polls as well as the chat box. So starting with the first question, what is the standard unit of the standard deviation of the vertical distribution of plume concentration? So the options are meters, meter per second, grams per second, and micrograms per meter cube. So I will drop the poll. Yeah, so we have around 10 people here. At least I should get 6 to 7 responses. Okay, some people are saying option D. Someone is saying A also. Okay. What about the polls? Okay. So I think people don't have clarity on this. Okay, we will see this in detail. No issues. Okay, I think now we have enough responses. Some people are saying A, some are saying B. Okay, okay, we'll see the answer. So, yeah, this is from lecture 1, Gaussian blue models. So there will be a slide where all the units are written. So you should go through that. That will also help you in solving the numericals, because many numericals there will be a lot of different parameters. So you should remember the units well so that you don't confuse the different units together and get the correct value, because sometimes a unit can be in centimeter but the other units may be in meter, so you will have to convert it accordingly. So yeah, here we are discussing so standard deviation of the, so this is not important. So this is just a mathematical term. We are worried about the vertical distribution of the plume concentration. So we'll have the plume that will be emitted. So it will be in a certain range. So there will be a mean point and there will be some of its standard deviation. So what is this? Basically, this is a vertical dimension, right? So this is nothing but height. So it will be in the dimensions of meter. So I think some people answered it correctly. I think most of you answered correctly. So yeah, it was fine. The correct answer is meters here, because here we are simply saying vertical distribution of the plume concentration. This is just to confuse you, standard deviation. So vertical distribution, how it is distributed. So it will be distributed vertically across in the space dimension, that is height. So that will be in meters. So I think many people were answering other options also. So we'll see them quickly. So if you take meters per second, so this will be of wind speed. So wind will blow, that will control the plume behavior. So wind speed will be measured in meters per second. What will be in grams per second? So that will be the emission rate. So how much pollutants? What is the amount of pollutants being released by the plume or the chimney per unit of time? That will be emission rate. And micrograms per meter cube will be the concentration. So per unit volume, how much pollutants are there? That will be measured in micrograms per unit volume. So this will be for vertical distribution. And yeah, and not just vertical distribution, but also if we'll have the horizontal distribution also, so that will be also measured in meters. So the correct answer is, I think most of you answered it. So yeah, option A, meters. I have told the other units also, so you should remember them. So option A, meters is the correct answer. Moving to the next question, question 2. Which of the following assumptions are associated with the Gaussian plume model? There is no diffusion in the longitudinal direction x, uniform continuous emission rate, the shape of the plume is conical, the pollutants are non-reactive gases or aerosol. So you have to choose the correct option. So for option A is 1 and 3, B is 2 and 4, C is 2, 3 and 4, and option D is all of them. So we'll drop the poll. Yes, so somewhat mixed response. B, C, D, everything is coming. What about polls? Okay, maybe we'll see the answer. No issues. So this question is also from lecture one only, Gaussian flow models. So we will see all the assumptions so that we'll just quickly revise all the assumptions. So first will be, so we'll assume a steady state, that is basically the travel time will be neglected for the pollutants. So we'll not assume any travel time. So we are assuming steady state throughout. Then we will have normal distribution, which we saw in the previous class also. So this will be assumed both in the y in the z direction. Third will be, we'll assume flat terrain. We'll assume a constant wind speed. Wind speed will not change. Then we will assume molecular diffusion. Actually, this will be one of the first ones. So this will be the phenomenon for dispersion, molecular diffusion. Then we will assume shape of the plume, which will be conical. Finally, we'll have the nature of pollutants. So that would be non-reactive. And yeah, along with the wind speed, so emission rate, that should be constant and continuous. Then there should be no deposition at the surface. So everything should be in the air. There won't be any deposition on the surface level. So these are, I may have missed one or two assumptions here, but I think I wrote most of them. So these are the primary ones that you should remember. So let's see now. So if you see there is no diffusion in the x direction, so I think I missed this one. Yeah. So y and z will assume diffusion, but in the x direction, that is the longitudinal direction, there won't be any diffusion. So this is one of the assumptions. So one is correct. We also discussed emission rate should be continuous and it will be on a like a fixed value uniform. So two is also okay. Shape of the plume is conical. So yeah, we discussed this here. So three is okay. And pollutants should be non-reactive gases or aerosol. There should not be any reactive nature. That is, if we are releasing two types of pollutants, it should not happen that the two pollutants are reacting together and forming a third pollutant. Any kind of that phenomenon, chemical reaction that we say, should not happen. So it should be totally physical phenomenon, that is molecular diffusion. So four is also okay. So we are left, I think every option is correct here. So option D, 1, 2, 3, and 4. All the options are correct. I think there was some mixed response on this question. So I hope you will revise these assumptions. That's why I've written everything here. So option D, 1, 2, 3, and 4. All the assumptions are correct for GPM models. Coming to question 3. So a relatively easier question now. So the comprehensive stock of all the pollution emitting sources and emissions in a given region with a specific time period is called emission inventory, emission factor, emission correction coefficient, and emission norm. We have some responses. So I think here people have some clarity. Most people are saying option A. Okay, I'll close the poll. We'll see the answer. I think yeah, everyone, almost everyone is saying option A. Okay, we'll see the answer. So yeah, even if you don't know like what is this answer, you can do it with logic also. So what we are being asked is the comprehensive stock. Stock is like it's basically a pile of items, right? And if you have, if you like somewhat technical term, but you would have heard like companies and industries, they will use what are the items in their inventory. So how much stock they have. So basically these two terms are synonymous with each other. So even if you don't know, you can make a educated guess and it will be emission inventory. Because here we are not talking about any factor. We are talking about a comprehensive stock. So it should include everything that is there. It cannot be a norm. It cannot be a factor. It cannot be a coefficient. So the most logical option here is emission inventory only. But to discuss the quantitative aspects of this. So what we do is we choose a specific time period. So we'll choose like a year or a month, depending upon our analysis, we can choose. And we'll consider all the pollution emitting sources. So this can include vehicles, industries. We can have other sources of pollution also, let's say construction. Uh, One of the major sources in India is power plants, coal-based power plants. So all of these sources we'll take the time period and we'll try to calculate how much is the emission from all these sources. So how this helps us is that we'll know that, okay, let's say we have simply we have 100 units of air pollution, out of which let's say 30 are coming from vehicles, 40 are coming for power plants, 20 from construction, 20 from industries. So we know that power plants are contributing the highest. So if we can act on this, we can reduce this. But if there is a source of pollution, let's say which is like very, I think 40. Okay, let's do this 10. Yeah, now it is okay. Or maybe let's do this 5 and another source 5. So instead of acting on the sources that are causing 5 units of pollution, a higher priority should be to act on the sources which are causing more pollution. So that's where emission inventory helps us. We can know what sources are causing more pollution and act upon them and evaluate our strategy and act on it. So I think everyone answered it correctly. So the correct answer is here is emission inventory. So that will be the stock of all the pollution emitting sources in a given region in a given time period. So option A, emission inventory, is the correct answer. Moving to the next question, question 4, the basic equation. So it is a continuation from the previous question. For emission estimation it is the difference of emission factor and activity data. It is the sum of them. It is the product and it is the factor division of them. And drop the poll. Okay. I think everyone is saying option C here. I think everyone is saying C. Shake the polls. Okay. Hmm, I think it's clear. We'll see the answer. So as we saw in the previous question also, so we'll have the air emissions. So that will come from different sources. So more technical term to use for this is activity. So there will be different activities happening, A1, A2, A3. And these activities will be happening at different scales. So there may be a large building getting constructed, a small building, a small house. So, but each of these activities will have a different emission factor. So a small house may not have that much emissions, which a large level residential complex construction will have. So we need to incorporate separate emission factors for each of them. So depending upon the scale of the activity, there will be emission factor. So the emission will be basically equal to this activity into the emission. And then what we will do is we can add all of these and we'll get the emission inventory basically. We'll get the sum total of it. So I think everyone answered it correctly. So emissions will be equal to the emission factor, which will be per unit of the activity. And then we'll have the activity data. We'll take the product of them and get the emissions from that particular activity. Correct answer is option C here, which is emission is equal to emission factor into activity data. Moving to question 5. So again, a unit based question. So the buoyancy flux parameter F, which is on the left hand side, is utilized to calculate the effective height of the stack. The formula for the buoyancy flux parameter is given below. So I have given the equation. So it is a G into Vs, which is exit velocity, ds by 2 whole square, Ts minus Ta by Ts, where Ts is exit temperature and Ta is the ambient temperature. So the unit of F is meter squares per second, meter to the power 4 per second square, meter power 4 per second cube, meter power 4 per second power. We'll drop the pole. Q4. Okay, this is Q5. Yeah. I think everyone is saying, almost everyone is saying option C. Right. So C. Okay. Most people are saying C. What about the poles? Okay. Okay. Maybe we'll just see the answer for this. Close the pole. I think almost everyone told the correct answer. Quickly see the. So what we'll do is we'll simply do a dimensional analysis. Since we know what are the other things, we can do this. So we have G, we have BS, we have ds by 2 whole square, ts minus ta by ts. So what we want is the unit of f, that is on the left hand side. So G is our acceleration due to gravity. So this will be meter per second square. Bs is speed, exit velocity, that will be meters per second. ds is diameter, so meter square. And then ts minus ta will be a temperature, ts will be a temperature, so it will be degree Celsius divided by degree Celsius. So this we can remove. So we will be left with meter power 4 divided by second cube. So yeah, so that will be the answer. That is the unit of F here. F is what? The buoyancy flux parameter. I think everyone answered it. Almost everyone answered it correctly. So I think it should be clear now for people who did not answer. So meter power 4 by second cube. So you can simply put the units of the other variables and get the unit of F. So the correct unit is meter power 4 second cube. Moving to question 6. To calculate the maximum concentration using the Gaussian plume model, sigma z is given as root h by 2, h by root 2, h by 2n, h by root 2, h root 2, the product. So this is question 6. Yeah, most people are saying option. Okay, some people are saying A, some are saying B also. Okay, okay. So mostly people are saying B. What about the polls? Okay, everyone is saying B. Okay, we'll see the answer. Not much to discuss here. It's a straightforward question. So yeah, if we want, basically this should be the distance to maximum concentration. So if we measure relative to the plume at what distance, we'll get the maximum concentration of the plume. So if you want to find that, so what should be the condition that sigma z by sigma y, this ratio, this should be constant, should not change. So at that value, at this when this condition is true, sigma z should be equal to h divided by root 2. So this should be the relation that should hold true. So this is called as distance to maximum concentration. At that value, what should be the standard deviation for z? That should be h by root 2. Then this value will hold true. So yeah, correct answer is option B here, which is h by root 2. So option B, h by root 2 is the correct answer for question 6. Moving to the next question, question 7. A part of the atmosphere, so theoretical question that behaves in a coherent way concerning the dispersion of air pollutants is known as pollution potential, atmospheric stability, ventilation coefficient, and air shed. So I've dropped the poll, you can respond there. Okay, people are saying D. Okay, so mostly people are saying option D. Okay, so I think everyone is saying D. Okay, yeah, we'll see the answer. So, easy question, just based on the definition of air shed. So yeah, air shed is nothing but like it's like a, you can say, a geographical unit. It will have similar type of air pollution characteristics and similar wind patterns or weather characteristics, we can say. So the weather characteristics should not change too much in a air shed. It should be consistent with time, and also the air pollution will be like, similar types of emission sources will be there, and like a pollution will be in a certain range, and wind pattern will also be consistent. So that region we can call as a air shed. So what will happen is, due to these characteristics, it behaves in a coherent way. Like, it won't be that certain times the air pollution will be very low, certain times it will be very high. It will be in a certain range that will vary concerning the dispersion of the air pollutants. So that is called as air shed. So these three are not the answers. So correct answer is option D, which is air shed. Yeah. So option D, air shed, is the correct answer. So it will be a geographical unit. So it can be a small community, very few houses, some one or two emission sources. It can be a large metropolitan area also. The size of this unit can change. So the correct answer is option B, air shed. Moving to question 8. So this is a numerical here. So I'll read it. Sulfur dioxide is emitted at the rate of 150 grams per second from a stack with an effective height of 60 meters. The wind speed at stack height is 5 meters per second, and the atmosphere stability class is D for a overcast day. Sigma y is given 38 meters, sigma z 19 meters. Ground level concentration along the center line at a distance of 500 meters from the stack needs to be found in the units of micrograms per meter cube. So the options are 40, 60, 90, and 100. So take your time, do it correctly. Okay, I've dropped the poll. You can respond there. Okay, we have one response, option A. Response for C, one response for A. We were getting around 6, 7, 8 responses per question. We will wait for one or two more minutes. We'll see the answer after that. Okay. So mostly people are saying option A, option B, and someone is saying C also. Okay. What about the polls? Some people are saying A, some people are saying C. Kind of a mixed response. Okay, okay, maybe we'll see the answer. No issues. Wait for a few more seconds in case someone wants to answer. Okay, I'll close the poll now. Okay, let's see the answer for this. So if we want to find the concentration of the pollutants, so we'll have to use a certain equation for that. So let's see first what is the equation, then we will substitute the values in this. So C will be equal to, so we'll have Q pi U sigma y sigma z. This should be taken as a product with exponential minus zero point 0.5 h by sigma z whole square. Okay, so this is the equation for the concentration of pollutants. So that's what we needed, concentration along the center line. This distance is not needed here. So it will be, so what is Q here? This is Q, 150 grams per second. Let's change the color to make it more visible. So this is Q here. We have the wind speed here, that is U. Height is given, stack height 60 meters. Sigma y is given, sigma z has been given. So let's put the values now. So concentration will be Q 150, pi, U is wind speed 5, sigma y 38, sigma z 19, exponential minus zero point 0.5 into h. H is given as 60 meters here, stack height. So 60 divided by sigma z, which is 19 whole square. Let's find this value. I need the calculator for this. Okay. So let's find the one on the outside first. That will make it simpler. Divided by 5. So this is coming out as 0.0132 into 60 by 19. Well, yeah, so just a second. So this is into the inside thing is coming as 6.833 maybe into 10 to the power minus 3. This whole exponential thing after calculating. This will come out as, it's coming out as 9.019 into 10 to the power minus 5. So since we need this in micrograms per meter cube, let's do one thing. Let's make this as 90.19 into 10 to the power minus 6. And here we are taking the emission rate in grams. So this will come out in grams per meter cube. So when we convert this to micrograms, so we'll take the product with 10 to the power 6. So this will become 90.19 micrograms per meter cube. So approximately 90. So that is the answer here. So 90 micrograms per meter cube. That will be the correct answer here. So I will stay on this slide for a few seconds so that if someone wants to note it down, you can note it. After that, we'll move ahead. So I think someone, okay, Pankaj had said option C. Okay, we have the correct answer there. Okay, I think one or two correct answers we had. So this is the equation Q divided by pi U, product of both the standard deviations into e power minus zero point 0.5 h by sigma z. So we'll take the vertical standard deviation and we'll divide h by that. Okay, so we'll move ahead. Somewhat long question. So yeah, answer is 90 micrograms per meter cube. Moving to question 9. So theoretical question. What is the product of maximum mixing depth or height and the average wind speed within the mixing layer for a given region? Ventilation coefficient, pollutant concentration, pollution potential, and atmospheric stability. So I will drop the poll. Okay. I think most people are saying option A here. Okay, we'll see the answer. I'll close the poll now. Yeah, so this is the answer is ventilation coefficient here. Option A, which is not much to discuss here. This is the basic definition. So what we do is the basic thing is first we need to take the mixing layer. So it should be within a mixing layer. We cannot change the layers. Within a mixing layer, what we do is we'll take the average wind speed and take its product with the maximum mixing depth or height. So the this will be given as V is equal to, so we'll take the maximum depth or the height, and this should be taken as the product with the average wind speed, and this will be the ventilation coefficient, Vc. So the correct answer is option A here, ventilation coefficient. Moving to question 10, the available assimilation capacity AAC is given as, so I've dropped the options here. So it is a permutation of permissible standard as per NACS and ambient pollutant concentration. So difference, sum, product, and division. Okay, see question 10. Yeah, so I think everyone is saying option A here. Okay, we will discuss the answer. This is nothing but, like, let's say we have the, so this is our, just a second. So let's say this is the standards as per NACS. So this is the permissible standard here. Let's say we have the air pollutant concentration at this level. So right now, let's say this is the zero level. So we have this much pollutant concentration in the atmosphere. What we can do is we can pollute it this much more so that we reach the standard basically. So this much more we can say margin of safety we have left. After that, we will start violating the standard and it will start affecting people, animals, flora and fauna, everything in the region. So this much of margin we still have left. So this margin is basically, the technical term for this is called, so this is available for us, assimilative and capacity. So this much amount of pollutants we can discharge more into the atmosphere without violating the standards and the use of the air resource. So we have the certain pollutant concentration. We can pollute it somewhat more to make it reach them. So that much margin of safety we have. I think everyone answered this correctly. So nothing. This is the permissible standard, and we have to simply subtract the ambient pollutant concentration. So if this value should always be positive. That is, we should always have some margin left. If this value is negative, it's a sign of danger, and we have to take action accordingly. So available assimilative capacity is difference of permissible standard and ambient pollutant concentration. So I think this should be clear. Option A is the correct answer. We have to take the difference between the permissible standard and the ambient pollutant concentration. Moving to question 11. What are the disadvantages of using the Gaussian plume model for area sources? Requires large amounts of input information, consumes large amounts of computer time, involves complexity. So we have to choose. Option A is 1, 2, and 4. So I think there is no 4 here. 1 and 3, 1, 2, and 3. This should be, let's correct this here. This should be 2 and 3. So drop the pole. Okay. So some people are saying option D. Some people are saying C. What about the poles? Okay. C and D. Fine. We'll discuss. So yeah, once we use GPM models, so what happens is we need a lot of data. Okay. So we need data on emission rates. We need data on weather. It is the wind speed, ambient temperatures. We will need data on sigma y, standard deviations, sigma y, sigma z, emission rates. We'll need data on the stack heights. And we don't need these for just one source. Since we are here considering area sources, so we'll do the calculation over a certain area. So if we have to calculate for a whole community, a whole city, so there will be thousands of sources that will be causing pollution. So to include everything in GPM, we will need a lot of parameters, a lot of data will be needed. So option one is correct to require a large amount of input information. That is obvious. Also, since we have large amount of input information, it will also consume large amounts of computer time. Because doing the calculation for just one source, let's say, it will take maybe 1 millisecond for a powerful computer. But once all of these variables start coming in from all sides, and this needs to be done in real time. We can't collect the data and do the calculation after 1 year. If we have to do some action, do some proactive approach we have to adopt, we need to do the calculations in real time and monitor it. That's how Google uses the AQI. So if you whether open weather in Google, there will be option to check the AQI. That's how they will collect the data from different sources and real-time calculation they will keep showing, and they will show the AQI of the city, and they will show these recommendations like use a mask, safe to go outside, some irritation may happen, something like that. A message they will show based on the AQI. So that's how they do it. They will do it in real time, but the amount of data that they will deal with will be huge. And just like, maybe time of 30 seconds can take for the code to run for a whole city. But this time is very high because that will lead to delay, like more and more delay, more data will come, more delay will happen. So to minimize this delay, so we'll need powerful computers, and this will consume large amount of computer time. So we have to optimize it accordingly. And also many variables are there. So obviously we saw the equation also. It is a very complicated equation. We have to do this again and again for thousands of sources. So it involves complexity also. So both 2 and 3 are correct. So option D is correct here. 1, 2, and 3. So I think some of the people answered it correctly. So option D, 1, 2, and 3. Moving to next question. Question number 12. So numerical we have again. So we have to estimate the total hydrocarbon concentration at a point 300-meter downwind from expressway on a overcast day. The wind is perpendicular to the highway and has a speed of 4 meter per second. Traffic density has been given along the highway, which is 8,000 vehicles per hour. Average vehicle speed is 40 miles per hour. Average vehicle emission rate is given. It's 0.02 grams per second. The options are 32, 42, 28, and 58. In all are in micrograms per meter cube. Okay. So I will drop the poll. Okay. We have two responses, A and B. Okay, maybe I'll give one more minute. We'll see the answer after that. Okay. Some people are saying A, some people are saying B. Okay, we'll see the answer. I'll close the poll now. So we need to find the concentration here. So first what we do is we have to calculate the number of vehicles per unit length of the road. So how will we do this? So we have the flow. So that is 8,000 vehicles per hour. So we'll divide this by the speed because we have the flow. So basically, I don't know how many you will know this relation, but flow on a highway will be given as density into speed. So the flow will be the product of the density into the traffic speed. So if we want the density, that is the vehicles per unit length. So we have to take the ratio of flow by the, flow by speed. So 8,000 vehicles per hour and speed is 40 miles per hour. So this is where we have to be careful with the units. So this will come out as 200 vehicles per mile, but we need it in meters, so we don't need this in miles. So 1 mile will be, let's take it as 1.6. So it will be 1 by 8. I think it will go to 0.125 vehicles per meter. Now what we will do is we will take the product of this. So this is vehicles per unit length. So we'll take the product with the emission rate. So that will give us 2 10 to the power minus 2, which is in grams per second, I think, if I'm doing it correctly. Okay, that is fine. So 2 into 10 to the power minus 2. So yeah, grams per second. This unit is okay. Then we have the vehicles per meter, which is 0.125. So this will come out as, let's do it correctly. So we have, yeah, it will be 2.5, and let's take it as 10 to the power minus 3 grams per second meter. So the vehicles part will go away because this is an average vehicular emission rate. So this will be per vehicle. So this will have vehicle per meter. So vehicle will go. So now we have the flow, not the flow, that is the emission rate we have, which will be per unit length. Now what we will need is the value of this sigma. So sigma z will be, so here we have been given 300 meters for 300 meters, and stability class is there. I think it is not there. Okay, so overcast day, stability class will be, I think, D we can take. So the sigma z will be 12 meters. So you can check the graph in the lecture. So that from the graph you can calculate this value of sigma z. So I think it is not given here. It should be given, but it's fine. Now we will need the equation. So for the concentration, so uh, yeah, estimate the total hydrocarbon concentration. So that will be C is equal to, so we have 2 Q. So Q we have calculated here, emissions by root 2 pi, which will be the constant term in the equation. And then we will divide this by, we have the sigma z here, and we'll take the average wind speed U. Let's do this quickly. So 2 into, so this will come out as 2 into, let's write this, 2 into 2.5, 10 to the power minus 3, root 2 pi. Sigma z is 12, and U is given as 4 meters per second here. So this is coming out as 4.156 10 to the power minus 5. Let's do this as 41.56 10 to the power minus 6 grams per meter cube. So again, same thing we'll do. We'll take the product with 10 to the power 6. So this will come as 41.56 micrograms per meter cube. You can round this off as 42. So the correct answer here is 42 micrograms per meter cube. That is option B. So I'll stay on the slide for a few seconds. Someone wants to note something down, then we will move ahead. Okay, we'll move ahead now. So yeah, correct answer is option B, 42 micrograms per meter cube. Moving to question 13. So in the downward direction from an air pollution source, with the increasing distance, the lateral and vertical dispersion coefficients will remain constant, decrease, increase, and initially increase and then decrease. Drop the poll. Okay. Someone has responded option A. Yes. No more responses. We'll see the answer. So yeah, if you consider sigma y, sigma z, all these will be a function of their corresponding mean distances, that is dy and dz. So since they are direct, and also x will be there, longitudinal distance. So as the distance will increase, what happens is the dispersion also increases. So all these factors will keep increasing with the distance, that is x. So here the correct answer will be option C, which is increase. With distance, since our distance is increasing, what happens is the both lateral and vertical dispersion coefficients, both of them will increase. So option C, increase, is the correct answer. Moving to question 14. The Gaussian plume model based estimations of the concentrations of a pollutant are not reliable beyond the radius of approximately. So the options are 15 kilometers, 20, 25, and 30. So I will drop the poll. Yeah. Someone is saying 20, someone is saying 25. Yeah, we will see the answer now. I think people are saying option C. I close the poll. So not much to discuss here in this question. So yeah, so when we apply GPM model, so it will maximum, we can say, it will be reliable up to 20 kilometers. So beyond 20, this reliability will be lost. So the reason will be like uh, the pollution sources will start interfering with any other pollution source. It will, like, interference starts between two different pollution sources. Wind speed can change over a course of 20 kilometers. Many other factors can change. So the consistency of the variables, their values, that will get affected. So that is why the model will only be reliable up to around 20 kilometers. So yeah, the correct answer will be, we can apply GPM model only up 20 kilometers from a certain source. After that, we can find obviously, but the results will not be reliable. So option B, 20 kilometers, is the correct answer. Moving to question 15. The expression for determination of concentration of a pollutant using GPM for a line source is given as, you have four options here, A, B, C, and D. So little changes. So drop the poll. You can quickly select which one is the correct one. think people are saying option C, option B. Okay, okay, we'll see the answer. I think most people are saying option C here. That is correct. So yeah, concentration if we need to find for a line source, we'll take 2q, we'll divide this by, so root 2 pi you should remember that will be there. So this was not here, it was not here. So we can remove option A, option D. Then we will have sigma z and wind speed. They will always come in the denominator. Exponential power minus h square 2 sigma z square. So we will build. So here we don't have q in the numerator, so we can remove this. So we are left with option C finally. So option C. So we have 2q by root 2 pi sigma zu into e power minus h square by 2 sigma z square. That is the concentration. So option C is the correct answer. So this is how we'll calculate concentration using GPM for a line source. So it will depend on the emission rate, standard deviation along the vertical, wind speed, stack height, and sigma z. So option C is the correct answer. Moving to question 16. So theoretical question: what of an environment, air environment, is the maximum amount of pollution load that can be discharged into it without violating the best designated use of the air resource in the planning region? Assimilative capacity, air shed, ventilation coefficient, and none of the above. So we discussed this in one of the previous questions. So I will expect a quick response. Maybe another 1 minute and we'll see the answer for this. Will not give a lot of time. This is a callback to another previous question. So I hope people will answer it correctly. So now I think we have 5 more questions, including this. Maybe another 15 minutes. We should be done. Okay. I think most people are saying option A here. Okay, fine. Okay, option A. I'll close the poll. Let's see the answer. Since we have already discussed this, I'll not give too much time to this question. So as we discussed, if we take this as our zero level, and we take this as the standard, that is the benchmark, and in somewhere in between, we will have the ambient air pollution concentration. So there will be a certain margin that will be left, and that much is the maximum amount of pollution load that we can discharge into the, and without violating the best designated use. That is without violating the standard. So this much margin we have left, this much more we can pollute the environment without violating our standards. So if we go beyond this, problems will happen. So we have to incorporate strategies there. So within this, we are fine. So that is called as available assimilative capacity. So basically we take the standard and we will subtract the concentration of the particular pollutant. So the correct answer here will be Option A, which is assimilative capacity. That much more of pollutant we can assimilate in the environment without violating the designated use of the air resource. So option A, assimilative capacity, is the correct answer for question number 16. Moving to question 17, what is an average representative value that is related to the quantity of an air pollutant released to the atmosphere due to a particular activity? Correction factor, activity data, assimilative capacity, and emission factor. So some of these questions will be callback to previous questions. So this way we'll cover some concepts. We'll also revise them in the class so that they will be clear. So we'll drop the poll. Okay, I think everyone is seeing option D. I'll give a few more seconds. We'll move on this question. Okay, no more responses. So we'll close the poll. Let's see the answer. Yeah, so as we discussed in one of the previous questions, so emission will be equal to emission factor into the activity data. So we have different types of activities happening in the city. So each activity will have its certain pollution level. So based on that, we'll collect data from different sources. And for each of these activities, we'll have an emission factor. And finally, we can take the product and sum all of them up to find the emissions that are happening over the region. So yeah, that will be the so emission factor is nothing but it is an average representative value. It will be related to the particular activity for the release of a air pollutant. So correct answer is option D here, is emission factor. Moving to the next one. So yeah, correct answer is emission factor. Question 17. So this will be the average value. So emission will be equal to emission factor into activity data. So coming to question 18. So the basic equation for estimating the emission from a particular sector is given as the product of so activity data and emission factor, activity data and concentration of a pollutant, emission factor and average wind speed, and emission factor and concentration of a pollutant. So maybe we can have some quick responses in the chat box. We'll move ahead. Okay. Okay. So I think everyone is clear. Uh, some people are saying D. Okay, I think we will see this again. So we have different activities which will contribute to air pollution. So each activity will have a different level of pollution. So that will be incorporated with the emission factor E1, E2, E3. Certain activity can have 1 unit of air pollutant per time, per unit of time. Another can have two, another can have three. So different factors we'll have to incorporate. And then depending on the scale of activity, we'll take the product. So that will give us as the emissions. And finally, we can add all these emissions up So that will lead to our emission inventory finally. So that's what we are doing. We are taking the emission from a particular sector. So that will be product of activity data and the emission factor. We cannot take concentration of pollutant or wind speed. These are not needed. So option A is the correct answer here. So we'll take the activity data from different activities. We'll take it and we'll take the product with the emission factor. So that would give us the basic equation for estimating the emission. So option A is correct, activity data and emission factor. Moving to the next one, question 19. So the equation for determination of concentration. I think this question, okay. C of a pollutant using the GPM model for a line source is given as, so we have been given the equation here. So the above equation is generally used if, so based on the condition we have to choose which is the right condition. So phi is 0 degree, phi is equal to 20 degree, it is greater than 20 degree and it is less than 20 degrees. So I will drop the pole. The responses. Okay, so greater than 20, two people are saying. Okay, so I think almost everyone is saying correctly. So we'll close the poll. So this is the relation that they will use for finding the, so relation has been given. So that is not our concern. So what they will do is they'll calculate this at angle phi. So what happens is if we take this angle to be very low, like let's say phi is very equal to, close to 0 degree. So what happens is, so this sine phi is in denominator. So as we know, if phi tends to 0, sine phi will also tend to 0. So if this tends to 0, the concentration will shoot up to infinity. That's why what we'll do is we'll take a threshold of 20 degrees and higher than that only we'll calculate. Because if we have seen let's just draw the sine curve here. So this is 0, this is 90, this is 180. So we can see that closer to 0, the value of sine will be very small. So this is y, this is x, so y is equal to sine x. So if we take closer to 0, value will be very small. So that is why the concentration will be artificially elevated. So that's why we will fix the value at 20 degrees and higher than that only we try to calculate the concentration. So that's the standard practice that is used. So yeah, phi should be taken as greater than 20 degrees. We'll not take it very close to 0. We'll take it at higher values. So C phi is greater than 20 for computation of concentration of air pollutant for a line source. So phi greater than 20. So this takes us to the last question for today's session, question number 20. So a relatively easy question. So emissions from what sector will represent the fuel combustion activities in households, including domestic cooking and the use of fireplace? Agriculture sector, industrial, residential, and transport. Maybe we can have some quick responses for this. Okay. Okay. I think we are clear. Not much to discuss in this question. So yeah, option C is correct here. So we are considering fuel combustion in domestic cooking. So domestic word itself should give you the hint that we are talking about residential sector. So whatever, like for if take for example urban, so we'll take use LPG for cooking, and rural places. Rural places also now most places LPG is only getting used, but if you go to some remote places, still wood may be getting used there because it is easier to find, cheaper. You don't need to do much. You will have to just collect it and you can use it. So yeah, so all these sources which are getting used for domestic purposes, so that will account to emission from the residential sector. If we have agricultural burning is happening, or some kind of dust is coming out from agriculture, so that will go in agriculture sector. Transport sector will have the emissions from the vehicles that we are using. Industrial sector, we have our factories which are operating, so that will release fumes. So different sectors, different types of sources they will lead to air pollution. So yeah, so with this we come to the end of today's session. So option C, residential sector, is the correct answer. So yeah, this was the last question for today's session. We are almost close to our time now, 6 p.m. Yeah, thank you everyone. Thank you for attending the session. So see you next week. If you have any doubts, you can ask. Let's we'll close the session in another minute. Previous year questions of this course. Okay. So you mean to say the questions from the exam or assignments? Okay. Exams, maybe you can ask in the discussion forum. The TAs will know it better. Just drop a doubt in the discussion forum. As far as I know, it will not be shared, but you can still ask. No harm there. Okay. Since there are no more doubts, we'll close the session here. So thank you for attending the session, everyone. See you next week. Have a great weekend.